Okay, hi everyone. So today we have the pleasure of having Robbie King from Caltech to present his work on exponential learning advantages with conjugate states and minimal quantum memory. Robbie, the floor is yours.
Thanks so much. Okay, let me just share my slides. I should also apologize for the record that I messed up and I thought that this was tomorrow based on the time zone. So my phone gave me a notification like half an hour ago. So I apologize if my slides aren't as polished as they should be. But hopefully it's okay. So I'm going to talk about a work that we did with Kiana Wan and Jared McLean, which is about a type of learning advantage using a new resource which we were able to uncover. And the title I've put here is Bosonic Learning using Row Tensor Row Star, and we'll see why the learning task we consider is related to bosonic physics, hopefully. Okay, so just a bit of background. Can you guys all see the slides, by the way, just to make sure?
Yes.
Okay, thanks. Okay, so just a bit of background. What do we mean by a quantum learning task? So by this I mean the data which we're going to learn from is in the form of a quantum state rather than classical data as we would be familiar with in classical machine learning. And this could come from a variety of different sources. Probably the most tangible near-term source of a quantum state will be a quantum simulation on a digital quantum computer. So for example, we run an algorithm, say Hamiltonian simulation, and we prepare an interesting quantum state. Suppose it could be the ground state of some material or some chemical molecule, or it could be the result of some time dynamics or something. And this state is a sort of many-body, highly entangled state, and we'd like to learn some interesting features of the state and to conduct physics. Another possible future source of quantum states is to coherently gather quantum data from a sensor and capture it and then transduce it into the quantum memory of our quantum computers. Although this one is slightly more not as near term because of this transduction requirement. Anyway, so you can imagine these quantum states which we want to learn from coming from multiple different places. You can also imagine that they will be expensive. So if you want to measure some properties of the quantum state, you would like to be efficient with how you use them because they are valuable and fragile. And in particular, one way to formalize this is that we would like to not require too many samples of the quantum state in order to conduct our task. How long do I have for the how long should I aim for, by the way?
I would say 45 minutes-ish. Yeah.
45. Okay, I might not have that much material, so maybe
Okay.
there'll be lots of time for discussion and
Okay.
questions. So feel free to stop me with any questions, by the way, as well, if anything pops up. Okay, so in this work, what we'll see is that there is a learning task. So a task of this form, you get some interesting many-body entangled quantum state, and you would like to learn some properties or measure something about it. And what we'll see is that if we are allowed to perform measurements, entangled measurements, on row tensor its complex conjugate state, so row tensor row star, then we need very, very few samples to perform this task. Yet if we only have access to row, not the complex conjugate, then even if we measure many copies of rho in an entangled basis, we still need exponentially many samples. So this is the new resource which I was referring to, which is the ability to entangle rho and rho star and perform a measurement. Now, rho star, I should say, is the complex conjugate state. So what does that mean? It means that I take the it's a basis dependent notion. So I take the density matrix and I just complex conjugate every element and I get another density matrix. So it's a different quantum state. And in particular, this complex conjugation is basis dependent. So we'll see in which basis we're talking about rho star. I should also say that now this begs the question: where are we going to access rho star from? So if your quantum data is coming from a coherent quantum sensor, it's sort of difficult to imagine how to get rho star because it's not a physical process to take copies of rho and transform them into rho star. Like if you wanted to do that, you would need exponentially many copies of rho. So rho stars are genuinely it's a resource that you need to have access to in the application. But one setting where you can access rho star is if your states are coming from a quantum algorithm on a digital quantum computer, because there, if you start in the all zero state and then prepare a state, you can simply complex conjugate every gate of the circuit, and this will naturally prepare the complex conjugate state. So I like to say this is a reason why you can imagine performing simulations of physics on a quantum computer could be advantageous to when compared to say running an experiment on the actual substrate, because when you have your simulation in your quantum computer, you have the ability to do these things, to prepare the complex conjugate. And here we show that gives you some power in a concrete task. Okay, is that all? Okay, with that, I'll move on to the next slide. Okay, so this is, I guess, more formally what I was saying. So given copies of an unknown quantum state rho, how can we learn it? So the first sort of notion that you can cook up if you were to try and write down this task is to learn the state in trace distance. So find a representative sigma, which is close in trace distance to rho, say epsilon close. But this is known to be very difficult. In particular, it requires d squared copies of rho if d is the dimension of Hilbert space. So this is very many. You can imagine d throughout will be sort of exponentially large. If you imagine sort of, for example, an n-qubit system will have d equals 2 to the n. But this is also often not necessary in terms of what we actually want to, the questions we are wondering about the state are more physical ones, such as, what are the correlation functions or the various physical quantities, and these take a different form. These are of the form expectation values of observables. So in particular, if we know the state to trace distance epsilon, then we know every observable to precision epsilon. But what if we have a list of observables, say S, which we are curious about, and this list is, we know this beforehand, then, maybe it's an easier task just to measure the expectation values of these observables. So this is a task known as shadow tomography. And what Scott Aronson showed in 2017 when he defined this task was that, in fact, only poly log D and log S copies of the state are necessary. So let's pause this for a second. So we saw before that to learn the state in trace distance, we need a d squared. So this is an exponential improvement in the dimension of Hilbert space, and it's also logarithmic in the number of observables, because of course you could measure one observable at a time, and this would give you a protocol which was linear in the size of S, but in fact this is logarithmic in the size of S. So this is first a very surprising statement. But this protocol has a few, pretty large caveats in terms of its practicality, such as it requires entangling many copies of the state, and it's very computationally inefficient. So you can ask, well, for sets S, which we care about from physical motivations, such as like bosonic physics or fermionic physics, etc., can we find ways of performing shadow tomography which is efficient in terms of how much quantum memory and entanglement you need, and also how much computational time you need. Because this result is actually for any set S of observables. It's a shockingly general statement, but of course has these caveats. Is this all? Maybe I'll pause here for questions.
If you guys have any questions, you can also type in the chat.
Okay. Okay, so how is this possible? So one way we can think about this is, what if the set S consists of commuting observables? Well, then we can see how we can achieve this very efficient sample complexity. Because what we can do is, if the set is, consists of mutually commuting observables, then we can measure in the simultaneous eigenbasis of these observables. And so this is some basis that we can measure in. And then every observable, we can just output the empirical estimate of its mean. And because the basis we measured diagonalizes all of these operators, we get a good estimate of each one. And to analyze this, formally, we would use something called the Chernoff bound, which states that if we take an empirical estimate with n samples, then we are exponentially concentrated in n. So the probability that we deviate by epsilon is upper bounded by some exponential in n and epsilon squared. In particular, you can then do a union bound over the whole set S of observables. And this will tell you that with higher probability, you get them all correct if you take enough samples. Okay, so this is sort of the sort of classical case, so to speak, right, when the observables commute. So what about a different case? For example, we can consider learning the expectation values of all of the Pauli operators on n qubits. So here the setting is we have an unknown quantum state rho on n qubits, and we'd like to learn every the expectation value of every Pauli p, so trace of p rho to precision epsilon. Now, the previous strategy doesn't work anymore because the Paulis don't commute with each other. Crucially, they are very non-commuting. So this sort of is a puzzle. How do we do this, right? We can't sort of capture all of them by measuring in a very clever basis, because all of the bases will miss a lot of the Paulis. And you can sort of formalize this intuition. And in 2021, these authors proved a result that says that if my protocol is restricted to only measure one copy of the state at a time, so in particular, the previous commuting case falls into this category, then to learn all of these Paulis, we need exponentially many copies of the state. So 2 to the n copies. Which sort of makes sense when you think about it, because we're gonna need exponentially many different bases to capture all of the Paulis. So how can we get around this? Well, the key is to consider entangled measurements. So what does this mean? This is when we take 2 or more copies of the unknown state and we perform a measurement, which is not just a measurement on one copy at a time, but it entangles them together and then makes a measurement. So here we're going to see that these sorts of measurements can be much more powerful at performing this shadow tomography task. So the key insight is that Pauli's, when they don't commute, they anti-commute, which means that if I braid 2 Pauli's, I get a minus sign. So what this means is that on 2 registers, p tensor p always commutes with p prime tensor p prime, because I'll braid the first 2, I'll get a minus sign, I'll braid the second 2, I'll get another minus sign, and they cancel out. So the set of operators p tensor p on 2 registers is a mutually commuting set of operators. In particular, there's some basis which diagonalizes them. In fact, we're back in the sort of commuting case that we looked at before, where we now have a commuting set of operators. What is this basis? It turns out it is the Bell basis. So the Bell basis on qubits 1 and 1 prime, 2 and 2 prime, tensored together, etc. So what is the protocol to perform shadow tomography on the Pauli's is that we take 2 copies of the quantum state and we place 1 on the first register, 1 on the second register, and then we measure in this entangled Bell basis. And this lets us simultaneously estimate all expectation values of the form trace of p tensor p times rho tensor rho, which is trace of p rho squared. So we can efficiently simultaneously estimate all of the squares of these expectation values. And then you need to worry about resolving the signs, but we probably won't discuss that today. So we can just focus on what are the absolute values, and this is how to get around this lower bound that we saw before. Okay, I'll pause here for questions because this is one of the key intuitions that's going to help us move on to the bosonic case where we need rho tensor rho star.
Yep. I think to continue. Yeah.
Okay. Okay, so operators which you can also consider forming a nice basis of Hilbert space, and in this case, we'll think of the Hilbert space as C to the D, so D-dimensional Hilbert space, rather than n qubits. So the Pauli's form a nice operator basis of the n qubit Hilbert space, but if we have a qdit, as they say, but a D-dimensional Hilbert space, a nice basis you can take is given by these clock and shift operators, or alternatively called Heisenberg-Weil operators. So it generalizes the Pauli basis, and so X is like this shift operator, and Z is this clock operator, where omega is like a dth root of unity. And in general, we can multiply them together, so we can have like x to the power of q, z to the power of p, and this gives you this so-called displacement operator, d sub q comma p. And here we're going to think of d as being very large, so exponentially large. So in particular, this is not just a sort of qdit version of the previous result where we have like n qdits instead of n qubits. Rather, we have a single qdit, but d is very, very large. And we'll see how this is the natural Hilbert space of if you want to consider a bosonic particle like a quantum harmonic oscillator or something. So in that sense, it's a sort of different limit to the previous qubit setting where we had n growing. Here d is the thing that is growing. Okay, and we can ask for the same thing. We want trace of d rho for every displacement operator d. Right, and I should mention that these displacement operators are not Hermitian. They're actually they are unitaries, but they're not Hermitian. So these expectation values will technically be complex numbers, but that's okay. Okay, so now I can state the main theorems that we have in our paper. So the first one is a similar result to what was previously shown for the Paulis, where if we use only single copy measurements, the number of states that we need to measure is at least the dimension of Hilbert space. So remember, D is an exponentially large thing. So think of it as like it's too many. It's impractical if we need, D copies of the state. By the way, I should say we can encode this D-dimensional Hilbert space in log D many qubits, right? Okay, so this is sort of not too surprising because this we knew this about the Paulis already. So, but theorem 2 says, okay, well, even if you have access to entangled measurements on rho tensor rho, or even further, even if you have entangled measurements on rho tensor rho k times, where k can be quite large, up to 1/12 epsilon. So this is in fact even growing as we require epsilon to be smaller and smaller. So if epsilon is 0.001, then we need, even if you have rho tensor 100, still the sample complexity is exponential. But the third theorem that we have says that if we are allowed to measure rho tensor rho star, where rho star is the complex conjugate state, then we can perform this task with log D measurements. So this is an exponential improvement. Okay, so why is this true? To see this, we need to look at the commutation relations of the displacement operators. So remember we saw before that if you braid two Paulis, you get a minus sign. Here, if you braid two displacement operators, you in fact pick up a complex phase, which will be a d-th root of unity. So it's no longer true that D tensor D commute on two registers, because if I square this complex phase, it won't become 1 necessarily. But it is now true that that these operators commute. So D tensor, in fact, it's transpose. Right. So you can think of this like another way of looking at this is that D tensor D star commutes with another D prime tensor D star prime, because if I twirl the first two, I get this complex phase, and I twirl the second two, I get the complex conjugate of the complex phase, and those two do cancel out. So I get a commuting set of operators. By the way, you can view these displacement operators in phase space as sort of unitaries which displace you in phase space. And this Q and P are sort of coordinates which tell you, how far to move in position and momentum space, respectively. This is the sort of way in which these operators represent a bosonic system. Okay, so now we can try to use the same trick as what helped us in the Pauli's case. But if I so now I have a commuting set of operators, say D tensor D transpose, but if I place rho tensor rho on my two registers and measure in, I should say that now, of course, similarly, they have a simultaneous eigenbasis because they all commute, which is the entangled eigenbasis given by this. This is the circuit way of looking at it, but it's just a generalization of the Bell basis, really. So instead of to get to the Bell basis, we would do a controlled knot and then a Hadamard. Here we're going to do a controlled shift operator and then a d-dimensional quantum Fourier transform, and this will take us to this generalized Bell basis. And this simultaneously diagonalizes all of these operators on two registers. Okay, so now suppose we measured rho tensor rho in this basis. This wouldn't necessarily help too much because what is trace of D tensor D transpose and then rho tensor rho? It doesn't really give you anything. But if we put rho tensor rho star on these two registers, then we naturally get trace of D rho squared as the thing that we can simultaneously estimate for all Q and P if it is. Okay, so this sort of shows you why you need rho tensor rho star, and this is in fact the our learning algorithm. So we take rho tensor rho star, we perform this entangling circuit, and then we measure, and this gives us some classical data that we can use to estimate all of these expectation values. Okay, so maybe this will be my last slide, but just to show where these displacement operators appear in bosonic physics. So if you imagine a bosonic particle, which is parameterized by phase space, so Q is position and P is momentum, then these Ds are displacements in phase space. And you can imagine, so this, for example, is common in optical physics. So you can imagine performing these sort of measurements in an optical setup, and there you can phrase the circuit that we give in terms of optical language, which I'm not sure if anyone here works on that sort of thing, but you know they talk about squeezing and quadratures and all of this stuff. So there's a way of viewing this in this sort of natively bosonic language. And or maybe I have one more slide, but I think this is not necessary. So I think I'll stop here and take questions if there are any. I realize this is a bit short, but hopefully that's okay. Oh, sorry, yeah, I couldn't hear you before.
Sorry. Yeah. So if anybody has any questions, please type in the chat or feel free to unmute your mic. So in the meantime, I do have some questions. So you said that your algorithm involves like a QFT inverse operation that kind of would you say that the intuition of this type of using conjugate states has anything to do with the act of converting to some sort of frequency spectrum from QFT, or is it like such learning algorithm has some other intuitions behind it?
Well, the intuition behind this quantum Fourier transform is definitely a sort of shifting from position to momentum space. But how does the complex conjugate state relate to this idea in your mind?
Yeah, I was wondering about if that has anything to do with like the conjugate space, the conjugate state itself being converted to some sort of momentum space. Does it have anything to do with the learning?
I don't know. Maybe there is an interpretation like that, but I think the thing that I would say is just if you look at the set of operators on two registers which commute that you can build from these displacement operators, these sort of don't naturally give you anything useful if you measure them on rho tensor rho.
Okay.
But if you measure them on rho tensor rho star, then they give you this useful information about the original expectation values. And by the way, we have a further result in our paper which says that this trick that sort of worked for the Pauli matrices and also worked here for the displacement operators, where you sort of take two or multiple copies of the Hilbert space and try and tensor together the observables to make them commute on many registers. This trick is sort of maximally used in this setting of these Heisenberg-Weil operators. So there's sort of a no-go result of using this trick for anything other than Pauli's and these things and a few other sort of generalizations. So yeah.
Okay. Okay. Let's see if Does anyone else
Yeah.
have any questions?
So, actually, may you introduce the final slide? So about the proof idea. Yeah. Yes, I'm quite interested to how you prove unit setting.
Oh, okay. Yeah, so this
Thank
slide
you.
is about how we this is how we show how we establish these oh sorry. Let's see. This theorem 1 and theorem 2. So in
Mhm.
particular, how do we establish these hardness results? Well, we reduce the learning task to a distinguishing task, and we show that you need many copies of the state in order to distinguish two situations. Oh, sorry.
Uh-huh.
And what are the states that we would like to distinguish? It's this ensemble. So we take a combination of two displacement operators by these complex numbers to get, and the reason we do this is so that this matrix E is Hermitian. And then we
Mm-hmm.
take the state, which is the maxi-mix state, plus an epsilon signal of this Hermitian E with a random sign. R is like a random plus minus sign. So this is a collection of states given by QP and the sign R. And the task is to, if I give you copies of this state versus copies of the maxi-mix state, which has no signal, you have to distinguish if I've given you this or the maxi-mix state.
So here, if R is only the sign, so will it make a difference? For example, if R is positive or negative, you just want to or is it the case that you know the epsilon and you just want to decide what is R?
No, it's actually I roll a random Q, P, and R,
Uh-huh.
and then I give you either copies of the state row given QPR row QPR, or I give you
Uh-huh.
the maxi-mix state, and you have to tell me if I've given you a state of this form or I've given you a completely mixed
I
state.
see.
And yeah, the intuition is that if the measurements on row are, if I don't have the complex conjugate state, then any measurement I can make will not differ statistically between measuring this state and measuring the fully mixed state. So if I, you know, if the statistical difference between these two is too small, that tells me I need to make, exponentially many measurements in order to pick up enough signal
Mhm.
to distinguish the two. That's the intuition behind the proof.
I see. Thanks. Yeah.
Yeah, and then yes, the key thing you want to show is this equation at the bottom where you say that the probabilities of, so L is sort of the transcript of the
Uh-huh.
experiment. Say I measure in this spaces, then it can even be an adaptive experiment. So L is the entire history of the measurements, and for any experiment, the probabilities are very close between these two if I don't have row star.
I see.
Okay. So I think are there any, if there's any more questions from the audience? Okay, yeah, I think we are good for today. Let's thank
Maybe I
Robbie
have
for,
another
okay,
question.
wait,
Sorry.
oh,
Yeah.
thanks.
So actually, there are a lot of results about quantum learning of a specific class of quantum states, right? Do you think there is any kind of possibility to unify these results or something like that? So recently, I noticed that like from the stabilizer in entropy, by using that property, you can somehow provide a lower bound for different quantum states. And for example, for the task like the direct decimation, and it gives a lower bound for the cloud shadow and other things. I'm quite interested in that actually recently. So I just actually from your mind, so do you think it is any possibility to kind of unify this kind of different class of quantum states about especially for the learning result? Yes.
Which classes of states do you think you have in particular?
I mean, so let's say we have a arbitrary quantum state, right? And now there are a lot of results for different specific class of quantum states. So like from the initially the Sabater states, and recently, for example, from our result, yes. I mean, there are kind of a series of results there. Do you think there is there any possibility to kind of unify all of the things together? So to find a property to quantify these quantum states.
Right. Well, what I would say is, okay, so for example, the stabilizer learning task. So it's like given a stabilizer state, make measurements to determine what it is. You can see how if you perform shadow tomography on Pauli's, this is sort of, a good thing to do for this task because you're trying to, this tells you what is the stabilizers. Because those will have expectation 1 and then the rest will have expectation 0 in particular. And also these states, for example, or these operators are the stabilizers of the so-called GKP code states. So there's this notion of GKP code on a bosonic harmonic oscillator. And one way to define it is it's stabilized by a set of displacement operators. So if you're given a GKP code state and you're trying to learn what it is, then perhaps these measurements would be helpful. So those are two connections I can immediately say. Yeah, and maybe that you can ask about deeper connections between learning specific classes of states and shadow tomography of certain classes of observables. Yeah, that's very possible. These are the sort of two immediate connections you can make, I think. Yeah.
I see. Yes, thanks. The last point is very interesting to me because I'm not familiar with GKP code. And yes, thanks. This brings the things somehow possible to me.
Okay. I think we're good for today. Thank you, Robbie, for giving this talk. And yeah, I think we are done.
Okay. Thanks so much for having me. Yeah, it was fun.